We live in an age of technological marvels. Every day, new innovations reshape our world, pushing the boundaries of what we thought possible. Smartphones fit in our pockets, acting as our personal assistants, entertainment hubs, and gateways to the digital universe. They connect us to a global network of information, allowing us to communicate, learn, and share in ways that were unimaginable just a few decades ago. Self-driving cars navigate our streets, promising a future where transportation is safer, more efficient, and accessible to all. Yet, on the horizon looms a technology so profound, it promises to dwarf all others: quantum computing. This emerging field could revolutionize industries and redefine the limits of human knowledge, but is it real, or is it just hype? The potential of quantum computing has been a topic of intense debate among experts. Quantum computing has been touted as the solution to some of humanity's biggest problems, offering computational power that could solve complex issues beyond the reach of classical computers. It could lead to breakthroughs in medicine, enabling the development of new treatments and personalized therapies. In material science, it could help create stronger, lighter, and more sustainable materials. And in artificial intelligence, it could accelerate the development of smarter, more intuitive systems. It could crack the codes that protect our online data, potentially rendering current encryption methods obsolete and forcing a complete overhaul of cybersecurity protocols. It could even unlock the secrets of the universe itself, providing insights into the fundamental nature of reality and the origins of the cosmos. But for all the hype, quantum computing remains shrouded in mystery. Its principles, based on the strange and counterintuitive laws of quantum mechanics, are difficult to grasp, even for scientists. The mathematics and physics that underpin quantum computing are complex and often bewildering. Its development is slow and expensive. Building and maintaining quantum computers requires cutting-edge technology and significant financial investment, and some experts believe that the challenges are so great, quantum computing may never live up to its promise. The technical hurdles are immense, and the path to practical, scalable quantum computers is fraught with uncertainty. So is quantum computing the next technological revolution? Will it transform our world in ways we can barely imagine? Or is it a pipe dream, destined to join cold fusion and perpetual motion in the graveyard of scientific dead ends? Let's explore further. The journey to understanding quantum computing is just beginning, and its ultimate impact remains to be seen. To understand the excitement, we need to grasp the basics. Traditional computers use bits. These are like tiny switches, either on or off. Quantum computers use qubits. These are strange beasts. They leverage the bizarre rules of quantum mechanics. Imagine a qubit not as a switch, but as a dimmer. It can be on, off, or somewhere in between. This in-between state is called superposition. It's what makes quantum computers potentially powerful. Now, imagine many qubits working together. They become interconnected in a way impossible for classical bits. This is entanglement. It allows quantum computers to explore many possibilities simultaneously. Think of searching a maze. A classical computer tries each path one by one. A quantum computer explores all paths at once. This parallel processing could lead to exponential speedups for certain tasks. This isn't just about doing things faster, it's about tackling problems impossible for even the most powerful supercomputers today. So why don't we have quantum computers on our desks? Because building them is hard, really hard. One major hurdle is maintaining superposition and entanglement. These quantum states are delicate. The slightest disturbance from the environment can destroy them. This decoherence is a major engineering challenge. Another issue is scalability. We can build small quantum computers with a few dozen qubits, but for practical applications, we need thousands or millions. Scaling up while maintaining qubit quality is a monumental task. Then there's the issue of quantum algorithms. These are specialized programs that exploit the unique capabilities of quantum computers. Developing these algorithms is a new field. We're still figuring out how to program these machines effectively. The technical hurdles are formidable, but brilliant minds are working on them. Progress is being made, albeit slowly. Section 4. Doubting the quantum dream, too good to be true. While some celebrate each step forward, others remain skeptical. They argue that the hype surrounding quantum computing has outpaced reality. Some critics point to the long history of unfulfilled promises. Quantum computing has been just around the corner for decades, yet practical applications remain elusive. Others question the fundamental feasibility. They argue that the challenges of decoherence and scalability may be insurmountable. Building a large-scale, fault-tolerant quantum computer may simply be impossible. Even if we overcome the technical hurdles, there's the question of cost. Developing and maintaining quantum computers is incredibly expensive. It's unclear if the benefits will justify the investment. This skepticism is healthy. It helps to temper unrealistic expectations and encourages rigorous scientific scrutiny. After all, extraordinary claims require extraordinary evidence. Section 5 Quantum Players, Who's Who in the Race. Despite the skepticism, the race to build a practical quantum computer is heating up. The stakes are incredibly high, as the first to achieve a fully functional quantum computer could revolutionize industries ranging from cryptography to pharmaceuticals. Tech giants like Google, IBM, and Microsoft are investing heavily in quantum research. These companies are pouring billions of dollars into their quantum computing divisions, hiring top talent from around the world, and collaborating with academic institutions to push the boundaries of what's possible. Startups and universities are also joining the fray. Institutions like MIT, Stanford, and the University of California are making significant strides, often in partnership with these tech giants. Meanwhile, nimble startups are bringing fresh perspectives and innovative approaches to the table. Google made headlines in 2019 with its claim of quantum supremacy. This was a monumental moment in the field, as it marked the first time a quantum computer had outperformed a classical supercomputer in a specific task. Its Sycamore processor performed a specific calculation in minutes, a task that would have taken a classical supercomputer thousands of years to complete. This achievement showcased the immense potential of quantum computing. This would have taken a classical supercomputer thousands of years. However, it's important to note that this calculation was highly specialized and not yet applicable to everyday problems. While impressive, this task was specifically designed to demonstrate quantum advantage. The real challenge lies in developing quantum algorithms that can solve practical, real-world problems more efficiently than classical computers. It doesn't yet translate to practical applications. Researchers are still in the early stages of understanding how to harness the full power of quantum computing for tasks like drug discovery, financial modeling, and climate simulation. IBM, another major player, is taking a different approach. Rather than focusing solely on quantum supremacy, IBM is working on creating a more versatile and practical quantum computing ecosystem. It's focusing on building a quantum-centric supercomputer. This hybrid system would combine classical and quantum processors to tackle real-world problems, offering a more balanced and scalable solution. This hybrid system would combine classical and quantum processors to tackle real-world problems. By leveraging the strengths of both types of computing, IBM aims to create a more practical and immediately useful technology. Meanwhile, startups like Rigetti Computing and IonQ are developing their own quantum computing platforms. These companies are often more agile and willing to take risks, exploring uncharted territories in quantum research. They're exploring different qubit technologies and architectural approaches. From superconducting qubits to trapped ions, each method has its own set of advantages and challenges. This competition is driving innovation and accelerating progress. The diversity of approaches ensures that the field is robust and resilient, capable of overcoming the many hurdles that lie ahead. It's an exciting time to be following the field. With so many players and so much at stake, the race to quantum computing supremacy promises to be one of the most thrilling scientific endeavors of our time. Section 6. The quantum verdict: breakthrough or hoax? So, is quantum computing the real deal or just hype? This question has been on the minds of scientists, technologists, and even the general public for years now. The answer, like the quantum world itself, is complex and nuanced. Quantum computing operates on principles that are fundamentally different from classical computing, making it both fascinating and challenging to understand. It's certainly not a hoax. The research and development in this field are very real, with significant investments and breakthroughs happening regularly. The principles of quantum mechanics are well established. These principles have been tested and validated through numerous experiments over the decades. And we've built small-scale quantum computers that demonstrate its potential. These early models have shown that quantum computing can solve certain types of problems much faster than classical computers. However, it's also not a magic bullet. The technology is still in its infancy and there are many hurdles to overcome. The technical challenges are immense. From error rates to qubit stability, the road to practical quantum computing is fraught with difficulties. Practical, large-scale quantum computers are still years, if not decades, away. The timeline for achieving a fully functional quantum computer that can outperform classical computers in all tasks is uncertain. It's crucial to separate the hype from reality. While the media often sensationalizes the potential of quantum computing, the scientific community remains cautiously optimistic. Quantum computing is a long-term endeavor. It requires sustained effort, collaboration, and innovation over many years. It requires patience, investment, and a healthy dose of skepticism. Investors and researchers alike must be prepared for the long haul. But the potential payoff is enormous. If successful, quantum computing could revolutionize fields such as cryptography, material science, and artificial intelligence. Quantum computing has the power to revolutionize entire industries. From healthcare to finance, the applications are vast and transformative. It could lead to new discoveries that benefit all humankind. Imagine breakthroughs in drug discovery, climate modeling, and beyond. So, while we temper our expectations, let's also keep our minds open to the possibilities. The journey of quantum computing is just beginning, and its future is still unwritten. Quantum computing may not be a hoax, but it's still a gamble. The stakes are high and the outcome is uncertain. Only time will tell if it pays off. The next few decades will be crucial in determining whether quantum computing will live up to its promise or remain an elusive dream.